Hello and welcome to part 2 of a video about using iPerf3. And in this second video, we're going to look at using iPerf3 when you have connections that have link aggregation and some of the peculiarities of that. But before we do that, someone asked something in the comment of the previous video that was a good question that I wanted to answer. They noticed that when I did, let's go over here, iPerf3-C 1.17.3. They noticed when I did this, and I ran the test over a 1 gig interface, and we'll let this finish, they noticed at the end that the reported number of datagrams wasn't the same. Oops, sorry. I have to do -u, otherwise this is pointless. So we'll do UDP, and again, we're going to do -B0 means do it as fast as you can, so it's going to hammer their interface with UDP. And at the end, an astute person noticed that these numbers were not the same. So it shows 0 lost datagrams, but clearly there were 9 datagrams that went somewhere that didn't make it here. And the answer to what happened to that and why it's different is there are a couple things you can do. One is that we could run this test with maybe a time of maybe 3 seconds. And then we'll go here and we're going to do a TCP dump looking for UDP packets going to the other machine. And then we can go back here and we can run the test. And it shows it did 247,820 were sent and only 786 on the other side. Go back to here. If you stop this, you'll see 247,822. So 2 more than what we sent. And sure enough, if you look at the data that was captured, if we look at the UDP, the first 2 frames, this is the sent, and then the one coming back is just a little setup message starts, and then it starts sending packets. So we did, in fact, send this many. And the reason why it reports a lower number here is because the iPerf program works by making a TCP connection first to the server to ask it to do a test. And when the client side finishes, and keep in mind the server doesn't know when the client side is going to be done. It doesn't tell it that ahead of time. It just starts sending. It sends over that TCP channel a note saying, hey, we're done. Give me back the statistics you have. And it turns out that that message over TCP beats some of the UDP datagrams that are still in flight. It's especially true because we're hammering the interface at full line rate. So on both the send and the receive side, likely all of the buffers are full. And the TCP message saying, hey, we're going to finish this test, send me your results, gets there before these last few messages. So these datagrams do get sent, they just don't get received because the other side terminates the test before they get received. So you're not losing anything here, and this does in fact mean that you didn't have any lost datagrams out of this number. There were just a few extra sent that weren't counted in the receive side. So nothing to worry about there, and it only does it if you are at pretty close to max line rate. If you do dash, I think it's K 100,000, I think that's right. So to do 100,000 datagrams, then it seems to always be pretty accurate. And I think it's because it may tell the other side that we're only doing 100,000 datagrams. And so it knows to stop at that. And so it ends up sending exactly what the other side expects. And then the numbers work. So just in case you notice that number and you wonder why it's different, it only happens on interfaces if you're really close to the threshold of the interface. If you go lower speed, it doesn't do it. So an interesting question and an interesting answer. But let's move on to talk about LACP and links. And so I did this iPerf3-C 10.1.17.3 in the past. And this, got me the 954 megabits, 950 megabits right on there of a single interface. And let that finish here. So let's add -P2. So we'll run 2 threads at the same time, both trying to just go as fast as it can. Let's see what happens. And we're getting 1 gigabit, so that's not any real surprise there. Well, let's try 4 threads. And now we're getting 2.3 gigabit, so we're going faster than 1 gigabit, right? which is a bit of a mystery. And so the question is, well, why are you doing that? And the answer is, if you look at our interface, sure enough, we have 4 1 gig interfaces bonded together in a bond, which is an aggregation group. And this aggregation group is using 802.3AD, which is LACP, to sort of talk to the other side. And it appears as one interface. So we have this interface that's 4 1 gig interfaces going to a switch that looks to us like it's one interface and that has this address. And you'll also notice that here you have this transmit hash policy, which we'll kind of talk about in greater detail, because that makes a somewhat critical difference. Now, both of these machines have that same configuration. And so when you run iPerf with 4, or let's try even 8. So if we do 8, we didn't get any more that time. We got 2.6, 2 point something. Let's run it again. 2.7, so not much difference there. Let's try 16 threads. And now we got 4 there, so pretty close to the maximum you can get. And so the question is, how can you debug the performance of an interface like this? And there are a couple things, and we're going to talk about it in a picture first. So let's do a little drawing. So, this particular setup, let's draw some boxes, has 2 machines that happen to be both configured the same way. And there is a little switch here in the middle. And each machine has 4 links going into this switch. And they're configured on both sides with LACP, so no difference there. And again, this is into one switch, so there's no other switches involved, no other transits involved. And each one of these links is a 1 gig link. And what is really interesting about aggregation, and in particular something like LACP, is that you have these 4 links. And the idea is that inside of the system, this kind of looks like one link. And one MAC address is assigned to this magical link that happens to have 4 physical links. And the same thing happens over here on the switch side. This is given one MAC address, but it actually has 4 physical links, and the same here and the same here. So when you're communicating from, this box here to this box here, it looks like a normal communication, MAC address of this, MAC address of that. It all works, it's magic. Little do you know there are actually 4 physical interfaces that interconnect these 2 different devices. And what's really cool about LACP is that it dictates a way you can negotiate and tell the other side that you want to have these links be aggregated, but it doesn't dictate an important aspect, which is that when you have a packet sitting here, and this packet, let's say, is destined to go to X, and it's from Y, and it's sitting here in a queue on this MAC address, and you have to decide, well, which link is it going to go down? And it's up to the algorithm chosen for this interface. So there is some algorithm here, some box that takes some inputs, and eventually gives you an answer that says, take that packet and put it down a particular link. Let's say that it goes down this link here. That makes it over to the switch. It pops out of the switch. It's into the switch logic here, which of course is looking at a table of MAC addresses, and it knows, hey, I got the MAC address I want to go to is on this little magical link over here. And what's important is that then on this side, there is another box of logic that depends on the hash algorithm for this switch that says, well, which link should this go down? And it will pick one. Maybe it's this one. And that little packet makes its happy way into X. So from Y to X, it may traverse this link and then traverse this link. But the algorithm used by the sending computer only dictates which one of these 4 paths it takes to the switch. The switch has its own algorithm for the path, the next path down. And it could be this is 4 links, could be this is 2 links, could be it's 1 link, but it's up to the switch to do that. And what's really interesting is that if this were a TCP connection, there are packets you send, and then there are packets that come back that include acknowledgements. When a packet is sitting here, and it's destined for Y, so it's going to go into here saying, hey, send me to Y. A set of logic over here that's its own unique logic will determine which link to use. And it may be a different link from the one the traffic came down on. It makes it back up to the switch, and then the logic in the switch here determines which interface to use for the traffic going back. And again, that could be an entirely different link. So sometimes you'll see people mention, if you Google pretty much any Reddit thread on LACP, someone almost always says eventually. Reminder, LACP is not load balancing, or something to the effect of 4 1 gig links isn't the same as a 4 gig link. That kind of commentary. And it's very true. But you often see people talk about flows, and they'll say that with LACP, you typically have a guarantee that a given flow goes over one link. And that is, use of the word flow is a little bit misleading, because it is true that a particular flow in one direction goes over one link. But a single TCP connection from machine Y to machine X may have one direction go over one set of links, and the other direction go over entirely different links, or the same links, or a mixture of those links. There's no guarantee that the return traffic comes on the same physical link, because at every juncture, it's up to the transmitting side to have its own hash policy. And that leads to the question, so, what's in this box? What are the hash policies? And I think in the olden days, the very earliest hash policies were things like the destination MAC address will be a good, simple policy, where depending on what MAC address you're sending to, you would pick a particular link. And that meant that if you went from machine Y to machine X, all the traffic would go over just one of these links. But if there was another machine, Z over here, that was somehow hooked up to the same switch, that might take a different path. So different machines could use different paths, but everything from one machine would use one particular path. Certainly it works. It has the downside that if, for instance, this box over here was actually the router going out to the internet, all the internet traffic from here is going to go to this MAC address first before going to the internet. And so you never really ever get to use more than one of these links for anything going to the internet. And so the idea is that this hash algorithm can be improved upon, and LACP doesn't dictate how you can improve it. And so there are other algorithms. One of them is, instead of just destination MAC, let's add in the source MAC. Oops. And let's also add in the destination and the source IP. So what's the IP address you're going to? And if we add that into the equation, then if you had, two web browsers on this machine, open going to two different sites, but all the way through this router, they could potentially take different paths because they have different unique IPs. So that is an improvement over that. And of course, this you would call layer 2, and this is layer 3. So this may be what you'd call layer 2 plus layer 3. And that's a good improvement over performance in terms of this machine being usable. The only thing would be that if you have a web page, and the web page makes multiple TCP connections to the same machine, they would probably follow the same link. And so you could also let's add on another layer, which is the port. And in reality, I usually mean port plus protocol. So TCP and UDP are given their own effective hashes. And so this is sort of a layer 4. And so sometimes you see it written as layer 3 plus layer 4. And if you remember on that previous screen, that's what it was on that computer, which means it uses the IP address and the destination port. And that means that, in theory, one program over here could be opening up a bunch of connections to a program over here on different TCP ports, and it may get to use more of these connections, depending on how the hash algorithm maps out. And you saw that when I had the 16 connections, because iPerf3 will make 16 different connections to 16 different ports on the other side, and so the source and destination ports will be a unique pair, and so that's why I was able to load balance those across the connections. But there's no guarantee, the algorithm itself doesn't guarantee that if you just pick 4 random ports, that those four ports will always hash to 4 unique values. It could be they happen to go down one or the other. And in fact, we can see, if I go back to the computer here, if we run this test, let's say with 4 threads, I have in a separate window here BMON running, which allows you to see the traffic on all 4 of those interfaces. And so if we run 4 threads, you can see that we're transmitting on just 3 of the links, and really twice on this link and then once on these 2 links. And we're receiving twice on that link, and then a little more on that link, actually. And so we were using 3 on transmit and 3 on receive. If we go back over to 0, maybe we'll make this 6 threads. And here, look at that. We're transmitting really more on these 2 interfaces, but receiving nothing on this one. So this interface is completely quiet. And this demonstrates the fact that on TCP, the packets going out and the packets coming back are not guaranteed to come on the same interface. And in fact, the loading was not unique. It was different for transmit than receive. And so that can make some really weird artifacts when you do dash bidirectional. Oops, do 2 dashes there. Because the traffic, you can look, it's somewhat, it's, summing on transmit at 281, but only 223 on receive. And the likely reason is that on the receive side, for some reason, it chose one channel a little more often, and so that channel was a little busier, and so it had less bandwidth overall. So you see an asynchronous bandwidth, even though those links are not at all asynchronous. It's just because there's asynchronous transmit hashing. So when you're debugging these, it can be complicated, and it's even more complicated if you consider that if this were actually 2 switches, because then there's a connection between the switches here, and if this was connected with 2 links between the switches, then you have a transmission control here and a transmission control here, all of which can be unique. And as an experiment, we can go back to here, and we're going to get rid of the bidirectional, and we run with -4. And we're getting 2.7, 2.3 gig per second, so pretty decent. It's using the links a little bit. If I bring over this window here, so this is logged into that Cisco router, and I can show how that router is configured. And this port channel load balance is a configuration, either system-wide or module-wide, that says for the LACP transmit hash algorithm, use this source dest IP L4 port, which means it's looking at both IP and port and protocol. And if we change this, so we could do, we can change it to, what's the default we can do? Oh, we could change it just to, let's trade to Mac. So let's go over here. So now we'll change it to use just the source dest Mac. Easy to do. Let's go back over to our machine, run the exact same test. And now we're stuck at 1 megabit because, of course, we told it on the transmit side, which for this switch means when it's talking to the other machine, and with the return traffic, always just based on MAC address. So it's never going to change. It's going to be stuck on one interface. And so now you're debugging it and you have far less bandwidth, all because of a very small change on the switch side. And if we were to go back over here and, let's see here, we're going to change this back to the IP L4, so it'll use the port and the source destination, both port IP. Then go back over here. We can try this again. And now we're getting a little more bandwidth. But notice we still only got 1.6 though. We didn't get the 2 we got before, but just run it again and we might get a little more. It depends on that hash algorithm and what ports count for what interfaces. If we use like maybe 8, we'll probably get it to use a little bit more of the bandwidth. Yeah, a little better there. So the big takeaway is that when you're doing debugging and there are aggregation groups, be very aware of how that transmit hash policy is set, both in the machines themselves, which is configured on, and if you're on a Linux, I think if you do procnet, I think bond, if I remember correctly. Yeah, you can see here, at the beginning of the bond, it'll tell you what the configuration currently is for that. And so it could be layer 2, 2+3, 3, 3+4, and 3+4 is sort of the best in some cases because it's going to look at the port number. And the same is true on the switch side. In some switches, you can't change it. I think in a lot of modern switches, you'll see this 3+4 at the default because it's probably the best in a lot of use cases because it allows multiple connections from one machine to another machine, same IP, to span them. There are occasions where in production, with a public facing, you may purposefully not want this because if you do it just based on, let's say, IP, not MAC address, then you can prevent one single IP from having traffic on more than one interface. And one other thing about the selection of these transmit hash algorithms, there are other ways to do it that could cause some problems. There is some support for algorithms like round robin, where Every packet just goes on whatever the next available interface is. And you can certainly do that. The only danger is that if you have it so that on a given connection, the packets can go on any one of the interfaces, then what will likely happen is you'll transmit something here, and then something here, and something here, and something here, and you might come back around here, and you get to the next one, and a packet you transmit here, which was supposed to arrive after one you sent here, may arrive before, and so you get a lot of out-of-order arrival on the other side. With TCP, that can cause some weird problems. It depends on how big the window is and how far out of order they are. If they're out of order by just a frame or two, then likely it won't make a difference. But if it's out of order by a lot, it can cause the other side to ask for retransmission. Obviously, with UDP, depending on how you implement it, some people might implement that it drops frames that are out of order. And so you generally wouldn't want to do a configuration like that. You can, if you know how your network stack is going to use it and you know what your protocols are going to do, you could do that. And it would guarantee a really good load balance. It just wouldn't guarantee in-order delivery. But the complexity really of the transmit in all four directions, I think, is perhaps the most, or the least talked about thing in regards to having links. If you have multiple computers with multiple links that are aggregated, there's a lot of variables that can change the order and the way and the speed you're going to measure. So just something to keep in mind when you're doing measurements with iPerf. That behavior would be the same with UDP as with TCP, with the minor exception that, of course, with UDP, there isn't a return path. So you'll see one behavior path, one set of transmit policies affect the traffic as it goes from one side to the other. So keep that in mind when you're doing your testing and playing around. And if you have any questions about how any of this works, be sure to put them in the comments, and I will happily make another video to answer them if we need to. Thanks a lot, and have a great day.